Hello, I'm Kubra Keskin and I'll be presenting my abstract realistic simulation of MRI metal artifact and field strength dependence. Metallic implants are used extensively to treat diseases occurring commonly at joints such as hip and knee or spine and many more body parts. Number of patients with metallic implants is increasing each year. There is an unmet need to better image tissues immediately adjacent to the metallic implants for patient follow-up and to identify possible complications. The biggest challenge in magnetic resonance imaging near metal is the susceptibility difference between metallic implants and human tissues, which causes vast magnetic field variations. For example, 12 kHz field variation for titanium, 58 kHz field variation for cobalt chrome can be observed at 1.5 Tesla. Magnetic field variations can change depending on size, shape, type, and orientation of the metal, and also field strength. Field inhomogeneity causes substantial artifacts such as signal loss due to signal dephasing or in-plane and through-plane distortions. All of the variables listed here can affect the metal artifact. Our purpose in this abstract is to demonstrate a simulation framework capable of simulating the effects of these variables. Our lab is particularly interested in imaging near metal at low field strengths, including 0.55 Tesla. Imaging at non-conventional field strengths will require re-optimization of imaging parameters, and simulations can help to do this efficiently. We start with the 3D XCAD adult male body phantom and digitally insert a 3D hip implant phantom with a cobalt chromium head and a titanium stem. We produce 3D tissue masks and then proton density and susceptibility values are assigned to tissue masks. In this work, only proton density weighted imaging is considered. However, other contrasts can also be simulated when field-dependent values of T1 and T2 are assigned to tissue masks. The susceptibility-induced field shift is calculated using a Fourier-based convolution method. We simulated a PD-weighted Merrick-Cassel sequence with phase encoding in the left, right, and anterior posterior directions. Simulated spectral bins images are combined with quadrature summation. Noise levels were calibrated using a reference dataset obtained with Merrick-Cassel at 3 Tesla. Additive bivariate Gaussian data was added to synthesize case-based data to match SNR of thigh muscle of the 3T dataset. Signal strength and noise standard deviation are then scaled accordingly. This figure shows a central coronal slice of the simulated Merrick-Cassel volume at different field strengths and with different number of spectral bins. All parameters are same except field strength and total number of spectral bins. As expected, the artifact size decreases for lower field strengths at the expense of SNR. Notice that extreme frequencies near the metal can be captured with fewer spectral bins at lower fields. Then we proceed with the imaging at 0.55 Tesla with 12 spectral bins to evaluate effects of readout bandwidth. Everything except the variable parameter is kept same. As readout bandwidth increases, blurring artifact reduces with a corresponding decrease in SNR. We also investigate the effect of RF bandwidth. As RF bandwidth increases, overlapping of spectral bins and therefore SNR increases. Wider RF bandwidth can be used safely at lower fields as SAR restrictions are relaxed. We use quantitative metrics such as artifact left-right extent, artifact area, and SNR to evaluate performance of Merrick-Cassel when different number of bins are used at various field strengths. This analysis can be used to evaluate and find sets of parameters that can give an optimum result for given constraints. Our initial MSI experiments with a hip implant phantom show a similar trend to the simulations at 0.55 Tesla and 3 Tesla. We also observe that our simulation results are consistent with the phantom results at 0.55 Tesla with different number of bins and readout bandwidth. In conclusion, this simulation framework can be useful for anticipating the performance of metal MRI at different settings and also optimizing the protocol and tailoring the parameters beforehand so that optimum performance can be achieved. Here we use a single example, one specific body phantom and a hip implant. However, the pipeline and methodology are general. As a future work, this framework can be extended to include different body phantom and implant configurations, different MSI techniques, B0 and B1 inhomogeneities, multi-channel acquisitions. Our initial simulations suggest that lower field strengths together with a high performance system could provide better quality metal MSI as long as SNR is carefully considered. Also, extreme frequencies near the metal can be captured with fewer spectral bins at lower fields. Thank you for listening.